Hi, so the topic today we are interested in is binary search. So we all know that binary search has a log n of time complexity, or more formally log base 2n. So it's kind of like this, log base 2n. This is the time complexity for binary search. And we also know that binary search is better than linear search. But in which case, right? In which case it's better? Well, the case holds for when the container or a piece of array is sorted, right? So for example, if I have an array and the array is in sorted order, right? And when I'm talking about sorted, there can be two ways it's sorted, right? So from low to high, so for example, ascending order, right? So it might be sorted in ascending order or it might be sorted in descending order. So you can kind of figure out, right? So when the array is sorted or it's kind of nearly sorted, then we can kind of use binary search and search any element or two elements, and we have a better time complexity than linear search. So it's a big of log base 2n, and we'll see the derivation or the explanation of the time complexity and the space complexity as well. Well, to explain binary search, in simple terms, we will be using 3 pointers. So for example, in linear search, we were using only 1 pointer and I named it as first pointer, right? So I'm just writing it in small, named it as first pointer. But in binary search, I'll be using 3 pointers. So let me just clear everything up here. So the 3 pointers in binary search will be start. This is the first one, right? This is the first pointer. The second one is end. And the third one will be mid pointer, or you can even call this as middle, right? The middle index. So initially, what will be my start pointing to? So just imagine that I have an array, right? So I have an array here, and this will be my initial index, right? 0, and this will be my final index, which will be n minus 1. Now, if you have watched the previous video of linear search, you might be knowing what n is. So n is nothing but the length of the array. So I'm kind of writing it as this. So len array, right? And the final index will be n minus 1. So initially, start will be pointing to the 0th index, and end will be pointing to n minus 1. Well, where will the middle index point to? So middle index is going to change dynamically. Well, this might be true to some extent, because when I said dynamically, I mean by runtime, right? So it kind of changes during runtime, but it's not really changing during runtime. It's kind of changing as the while loop or the for loop, whatever the case may be. So we are going to use while loop for this approach. You can kind of figure out the recursive approach once you know recursion and you understand the while loop approach. So in the while loop, as we go ahead, right, as we proceed further, we can kind of compute the mid values for different start and end indexes. Okay, and how is mid going to be computed? So mid is going to be computed as start plus end minus start by 2. Well, you might be confused with what I'm doing here, right? So let's just break this down. So my mid here is nothing but start plus end minus start by 2. Let me just open up the brackets here. So this should be start plus end by 2 minus start by 2. Well, start minus start by 2 should be start by 2 itself. So this is start plus end by 2. And I can kind of take out the half outside. So I can kind of write it like start plus end by 2. Well, you can see here that just by looking at this equation, we can figure out that mid is nothing but the middle index between start and end, right? So if my start is at 0 and end is at 4, so that should be 0 plus 4 by 2, so that should be 2, right? So why am I not writing start plus end by 2 simply, and I'm writing the equation like this? What is the reason behind that? Well, the reason behind that is because of the concept of integer overflow. Well, in Python, I generally write the code in Python. there is nothing as such, there is no problem. But in languages like C++, C or Java, there might be a candidate for the integer overflow condition. So what I'm talking about is, what if I'm using this thing, right? So I'm using start plus end by 2. Now there's no problem up till now, right? So for example, if my start value is 0 and end is actually 4, so this should be 0 plus 4 by 2, and that's 4 by 2, which is actually 2, right? I'm just kind of showing the mathematical way. But what if the start value is 4 and end value is also 4? And what if the system I'm working on, so let me just write it clearly, and the system I'm working on, just imagine, right? Just imagine the system I'm working on can at max display the numbers less than equal to 4. So for example, my system cannot display 5 or 6 or 7. They cannot display these numbers, right? Any number greater than 4, it cannot display. Just imagine a situation like that, okay? So what will happen now is, when I compute this, right? So when I compute this, so this should be what? 4 plus 4 by 2, and this should be 8 by 2. Well, you might be saying that, well, I have 8 by 2, so this should be 4. That's not an issue. But just at the back end, right? So at the back end, when the computation or the calculation takes place, it kind of sees that 8 is coming, right? It kind of sees that 8 is coming. And I know for a fact that my system cannot display any number which is greater than 4, right? Which I mentioned. Just imagine a scenario like that. Then in that case, I'm going to have a condition which is known as integer overflow, or you might just simply refer that as overflow, right? So I'm going out of bound. I'm going out of my limitation. So for example, I as a person has a capacity to work this much, but I work this much, right? So that is out of my capacity, right? So I might be having stress, or I might lose my emotions, and then so on, right? So I'm going out of my bound, right? So this is my out of the comfort zone, right? And this is my comfort zone. So this is something which is happening with the system here. So you don't have to be having this condition, the integer overflow condition. Just to avoid this, I'm using a simple modified equation. What is that? It's start plus end minus start. Let me just write the S here, by 2. So what if the start and end values are 4, right? So this should be 4 plus 4 minus 4 by 2, and this should be 4 plus 0, so that's 4, right? So we kind of get the same answer there. So there was 8 by 2, and that was 4, right? So that was 4. But over here, the system was not able to display any number which was greater than 4. So up here, there was an integer overflow condition, but up here, we have nothing as such computed as 8. So we kind of overcome that factor, right? Now that we have understood the integer overflow condition and how we compute the mid, let's just calculate the base thing, right? So how the while loop is going to go about. So our while loop is going to go like this. So while my start index, which is at 0, is actually less than equal to the end index, which is at the end. And then we are going to compute mid here. So mid will be nothing but start plus end minus start by 2. Well, now here there will be 3 main conditions, according to which my start and end values are going to get updated. Now imagine that I don't even know the conditions. Well, I know as of now, but just for a naive approach, how will I approach the problem, or how will I develop these conditions? Well, since there are 3 conditions, so I would like to take 3 different arrays. I mean 3 arrays, but they all will be same, right? So I will have to draw it 3 times. So for example, just going to take a small example here. So that's one array, that should be second array, and this should be the third one. So let's just have 1, 2, 3, 4. Let me have one more. So that's 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I think that makes sense. So let's just have the numbers in sorted order. So 10, 11, 12, 13, 14 and 15. I'll just repeat the process. And I believe we are done here. So imagine that we have to search 3 different numbers in each one of them, right? So let me just quickly write the indices. So that's 0, 1, 2, 3, 4 and 5. That's 0, 1, 2, 3, 4 and 5, and that's 0, 1, 2, 4 and 5. I think this 5 is looking like an S, but that makes sense. So for the first array, right, I'll derive the first condition. From the second array, I'll have the second condition, and from the third one, I'll have the third condition. It's as simple as that. So what if the number I'm searching for is 12, right, in this case? And in this case, for example, the number I am searching for is 10. And in this case, the number I am searching for is 15, right? So I'll just quickly highlight the numbers I'm actually searching for. So that's 12. In this case, it's 10. And in this case, it's 15. So you kind of have an eye on the number, right? And where we are going ahead with. So initially, my start will be at 10. So I'm representing S as start, and my end E, in fact, I'll just write it properly. So my E is nothing but end, and M is nothing but mid, right? Now my start is at 0th position. My end will be at the end position. So that's E. So 0 plus 5, right? So 0 plus 5 by 2. I mean, I'm just calculating it roughly over here. You should be calculating with the formula. So that's start plus end minus start by 2. So this is nothing but 2. Why? Well, I could have used 2.5, but I'm using the floor value and in the terms of integer. So that's 5 by 2 will be 2, right? So my mid will be at the second index. Now I'm seeing that the element at the middle index in the array, right, is actually equal to the number. So that brings us to our first condition. What is the first condition here? So my first condition will be that if the middle number is equal to the key I'm searching for, then in that case, I'll just set a variable like found is equal to true and then break out of the while loop. So this is going to be the key condition when I'm working with binary search, because this is the condition which is going to tell us that the element is present or not. So I'm kind of figuring out that if my middle index is actually equal to the key, then I'll just set my variable found as true, and then I'll break out of the condition, right? Let's just go ahead with the second one. So the number I'm searching for here is 10. But how do I derive the condition? Well, we derive the condition by following step-by-step approach. So my start is at 0, my end is at 5, and my middle will be at 2. How? Well, we have seen this here, right? I mean, we have seen this here, right? So seen this here. So now, as you can see that the middle index has an element of 12, which is actually greater than 10. So up here 12 is greater than 10. Up here 12 was equal to 12, right? So 12 was equal to 12. Up here 12 is greater than 10. But what is really 12? 12 is my middle number and 10 is the key. So where do I need to search in the array now? That's the main question. So notice carefully what I'm trying to say here is that I'll just use a different color. So if I know for a fact that 12 is greater than 10 and the array is sorted, that's the main key here. So definitely my answer will be lying on the left hand side of the array or the left part, and I will ignore the right part. I'll ignore the right part. So how do I move my attention towards the left part? How do I do that? Well, I simply leave the start pointer as it is. So where it was, I don't disturb it, right? And I update my end value with 1 less than mid. So 1 less than mid will be 2 minus 1. So that's 1, and my end will come here. So that's how the update will take place, if that makes sense. So this brings us to our second condition, that if my middle number, right? So if my middle number is actually greater than the key I'm searching for. So in this case, 12 was greater than the key 10. then in that case I'll update my end as mid minus 1, and I'll leave the start where it was, so I won't disturb start, right? And this is all about it. So this is the second condition. Now for the third condition, you might have figured it out already, but if you have not, then I'll just guide you. So this is the start pointer and this is the end pointer. This is going to be the mid pointer. And I know for a fact that my current middle number, which is 12, is actually less than the key or the number I'm searching for. So that's 15, if that makes sense. So where should I shift my attention in the array? Well, I'm seeing that since 12, the middle number or the current number is less than the key, and the array is sorted, that's the key here, I'm saying again that the array is sorted, then in that case I know for a fact that my answer is going to lie on the right hand part of the array, and I'm interested in the right hand side part. Well, which is the part I am going to neglect or ignore? Well, it's the left hand side which I'm going to ignore. So how do I shift my attention to the right hand side? Well, I'll just leave the end index as it is, so I won't disturb it, let him sleep there. I'll kind of modify start. Well, how will start modify? So start will be 1 greater than mid. So start will be pointing to 2 plus 1, so that's 3, and start will be updated here. And you might have figured out the condition. So this is going to be looking like this. So if my middle number, right? So if my middle number, so I'm not writing the number properly here, so I'm just kind of writing num just to make sure we are in bound. So I'm seeing that my middle number is actually less than the key. So my middle number is less than the key. Then in that case, my start will be updated as mid plus 1. And that's the end of the binary search here. As simple as that, right? So for example, I forget the concept of binary search, then I can simply draw 3 test cases here and kind of change the numbers on our own, right? We can kind of change the numbers or modify the numbers we have to search for, and then simply we can get the conditions. So how do we write the pseudocode? Well, you might have figured it out, so let me just write it in green color. So the pseudocode is going to look like this. So I will have a found variable as false initially, which means that I'm just going to write it a comment here, kind of like a comment thing. So which means that it means we have not yet found the key, right? Or key or the number we are searching for. I'm just going to denote it as key. So it looks good, right? So that's key. And my start will be at 0. So my start will be at 0. My end will be at where? N minus 1. And definitely in the input section, there will be an array, right? So you can kind of make sense. And N will be initially length of the array, right? So I'm going to write here, no, pay attention. So while start is less than equal to end, well, what is the first thing I'm going to compute? The first thing I'm going to compute is mid. So I'm going to write mid is equal to start plus end minus start by 2, right? It's as simple as that. Well, how do I know that which condition I have to check for first, right? You might be wondering that, okay, we have derived 3 conditions, but how do I know that I have to check for which condition first? Well, a surprising fact or interesting fact here is that you can check for any one of them. So let's just begin with the first one. So that's the first thing I'm looking for. So if, well, before writing the if conditions, I can kind of compute here that my middle number, right? So my middle num is actually what? Array of mid. It's as simple as that. So this is where the first condition kicks in. So I'm just going to write first condition, right? This is my first condition. So this is kind of like a comment section, right? So the comment line. And I'll check that if my middle number, this is the best case I want, right? So this is something I want to happen. is equal to the key. So key is something which will be given in the question, or you have to input it, right? So it's going to be user input. Then I'm going to set my initially declared found variable, which was false, to true. And then I'm going to break. Well, for computer science purpose, if you don't know about break, so break is going to break out of the entire while loop, right? So it's going to break out and then kind of do the further operations. So it's something which you have to learn on your own. So break and continue are kind of important. Now, what about the different conditions? Should I begin with if, or I should begin with else if, right? How do I do that? Well, definitely I have to begin with else if. So I'm going to write else if the middle number, so it's going to be middle number, is greater than key, right? So if the current middle number is greater than key, then I have to go, I'm interested in the left part. So how do I go to the left part? Well, the easiest way is to set the end value to 1 less than mid. So that should be mid minus 1. And guess what? What is this condition? Number is going to be second condition, right? So this is my second condition. This is my, just right up here. So this is my second condition. And now we are left with the last condition. So do I really need to write else if? Well, I can just simply write else, right? Because just imagine by yourself that if my middle number is equal to key, then that's the first condition. If my middle number is greater than key, that's my second condition. Then at the end of the day, I'll be left with only one condition, which is my middle number is actually less than key. So this is my third condition. And in third condition, I'm interested in the right hand side of the array, right? So the right part. Now, how do I actually go to the right part? It should be start is equal to 1 greater than mid. So mid plus 1. And I hope that makes sense. So after the execution of the while loop, right? So after the while loop kind of gets over, I'll check that if found, right? So this is going to check that if found is true. Then in that case, I'll just simply print that whatever the printing statement in your language is, you can use that. So I'm just going to print here that yes, found the element, right? So kind of print yes. Else I'm going to print maybe no, right? So I hope that makes sense. And I guess I just messed up on the print thing. So this should be print. And this is how the entire binary search algorithm works. Well, you might have seen the binary search algorithm kind of has a big O of log n time complexity. Well, in the linear search, we kind of saw that why it was big O of n, because we have to traverse the array entirely. But why is it not something like n by 2 here? We'll see that. So I'm just going to try to explain it in short here. So imagine that this is my array, right? This is my array. Now at step 0, right? So at step 0, when I'm doing nothing, so what is the length of the array? Well, the length of the array, as currently I can see, it's n. So at step 0, my length is what? My length is n. So I'm kind of writing here steps, and this is my length, if that makes sense. I'm pretty bad at drawing tables, so you can excuse me for that. And at step 0, my length is n. Now at step 1, well, what do I really mean by step 1? When I compute my first mid. So at step 1, when I compute, for example, my mid is here, right? So this is my mid. Then what is the length on either side of the array? The length on either side of the array is n by 2. You can see here, right? So that's n by 2. So I'm going to write that the length on either side is n by 2. So I'll more formally write this as n by 2. Now at step 2, you might have figured it out that what will be the length here. So at step 2, if I go to the left or the right, so for example, I go to the left part, so my mid will be up here. And what will be the length? This should be n by 4, right? This should be n by 4. Or I'll write it over here. So this should be n by 4. It's raining outside and I'm feeling glad that I'm making a video at this point of time. It's 4 a.m. right now. So this should be n by 4, and this is going to update here n by 4, and this is going to continue, right? So this is going to continue for some arbitrary steps, I would like to say. So at some step last, right? So at some step last, so this is the last step, right? What will be the length? Well, you can kind of dry run the code and then see that at the end of the day, we will be left with one block, right? We'll be left with one block. So what does really one block mean? Means the last step, what does really one block means? Which means that the array length is 1, right? So that's one length. So at the end of the day, I know for a fact that the length will be 1. But how do I actually derive some equation from here? Well, if you see that the lengths can be more formally written as this. So I am going to write the length as n by 2 to the power of the step number. So this should be n by 2 to the power of 0, which is 0 is nothing but the step number. Here it will be 2 to the power of, I'm just going to write it properly. So it's going to 2 to the power of 1. 1 is the step number. So up here it should be n by 2 to the power of 2, which is nothing but the step number, right? So 2 to the power 2. And this will continue, and this should be n by 2 to the power of last. And I hope that makes sense, right? So what if I was at step 3, right? Just for a quick revision. Then what will be the length? So this should be n by 2 to the power 3. And then so on, this will continue. So that's why n by 2 to the power last. Now I know that n by 2 to the power last is actually 1. So let's just keep this all aside and try to write this. So n by 2 to the power last is actually 1. I'll just kind of try to simplify here. So this will be n is equal to 2 to the power last. And then I'm going to write here applying. So this should be applying log on both sides. So what will this do? So this will be like log base 2n and log base 2 to the power last. Now you can figure out that this is 2. So last will come up here. So this should be last multiplied by log base 2 is 2. Now when I was doing this derivation for the first time, I kind of got confused, but this is something you might face here. So how do I handle this? Well, this is plain maths, so plain logarithmic maths. So if I have a log a base a, then it's always 1. So log 2 base 2 should be always 1. Well, consider a value as 2. So what will this be? So this will be log base 2 2, which is actually 1. So up here I can kind of write this as log base 2n is equal to last multiplied by 1, and I hope that makes sense. So just reversing the equation here, so last is nothing but log base 2n, and this is my final derivation for the time complexity of binary search. Right now you might be countering me with the fact that how are you telling that last is my time complexity, right? How do you say that? Well, you can kind of figure out from the steps here. So at step 0, which is the first time at I meant to say that timeline, right? So kind of if this is my timeline and these are my some points, so this is my step 0, right? And this is my, for example, step 25, right? And then so on till I reach some step last. So these steps are kind of representing a timeline, right? So these steps are kind of representing a timeline. And that's why at the worst case or the last case or the end point of the timeline is having a time complexity of log base 2n, and that's what is the time complexity of binary search. Well, in binary search, again, you can kind of ignore the memory used by the variables. So for example, variables like found, start, end, or the mid, So again, we can see that we have a big O of space complexity. For what? For binary search, right? So that's space complexity. I hope that makes sense. So we kind of figured out in this video that how the pseudocode can be written. Like, for example, what if I'm writing, what if I'm encountering a binary search problem and I forget the conditions, right? So what were the conditions? These were the conditions. So this was the first condition, this was the second condition, and this was the third condition. What if I forget them? Then we kind of learned that how we can derive them, right? By making 3 test cases. Even you can make 5 test cases, but at the end of the day, you will have 3 unique conditions here, right? And we saw how it's big O of 1 space complexity and a big O of log base to n time complexity, right? Now, notice one thing, that what if you are given a problem, right? So what if you are given a problem wherein you are having an array, okay? And the array you have is like this: 5, 4, 11, and then 2, and then 1. So you can kind of see that the array is not sorted. So what if I say that you have to find? So there are 2 cases here, right? So there are 2 cases. Just pay a little attention and you will be free with the video. I think I have taken a lot of time, so that's a bad sign on my part, but let's see. So there are 2 cases. So what if I tell you that you have to find one number and you have to do it optimally, definitely, and the numbers are given. So for example, the number should be like this. So for example, the number you have to find is 5, and in the other case, that's only one number. In the other case, you have to find various numbers. So you have to find 11, 5, and 1. Well, what will be the best way to go about proceeding this scenario, or to do it optimally? Well, one best way would be to, let me just get the windows closed here, or else it's going to interrupt with the noise part. So what's going to happen here is that you are seeing that I'm having only one element to be searched, but up here we have 3 elements, and the array is also not sorted, right? So in this case, because I know that I have only one element to be searched for, I'll use linear search because the array is not sorted, right? But in this case, I'm seeing that we have several numbers we have to search for. So the best way I could do is I would first sort the array, right? Sort the array. So that's my first step. Up here only my first step was the last step. So this is linear search, and then I'll find the element. And then I'll find all 3 elements in log base to n time complexity. And I think that will be an optimal approach, right? So if you are given any unsorted array and you are asked to find one number or 2 numbers, then you can kind of use the linear search method. But what if the number capacity or the numbers you have to search for are more than 100 or more than 1000 or more than 10 to the power 5? Then you have to be having, you have to sort the array first. So that's like, I think that should be a better sorting algorithm will be n log n, and you can kind of use your inbuilt sorting function. So I think that's arr.sort, and actually this sorting function which is inbuilt is known as timsort. You can kind of search it in the internet, you can kind of search it up the internet. So timsort is a very efficient algorithm, kind of takes an n log n time complexity. So this is how you should be proceeding, and you should be analyzing the questions properly, right? So in this case, I saw that there was one element, so I did linear search. But what if I had to search 100 elements, right? And the array is unsorted. Well, I just do one sorting and then kind of have the benefits of the binary search here, right? So I hope this video was helpful, and sorry for the little noise disturbance because it was raining outside, and I will meet in the next video with any other topic.